Electricity. We take it for granted. We cannot imagine modern society without it. From the coffee machine to the computer. From the lamp to industrial plant. Nothing works without electricity. But what is electricity? Let's make a comparison. In pneumatics, air is the source of energy. In hydraulics, it's oil. In electricity too, there's an energy source, but it's invisible. It's called electrical current, or more precisely, the electron current. There are three terms that everyone knows that define an electric current: voltage, current, and resistance. Voltage has the symbol V and is measured in volts. A rating plate on all electrical devices indicates with which voltage the device is to be operated. The current has the symbol I and is measured in amperes. The rating plate also indicates how much current a motor consumes. And finally, the resistance has the symbol R and is measured in ohms. This value indicates the resistance with which a load opposes current flow. These three variables are mutually dependent. And this can be expressed with a simple formula. V equals R times I. In other words, voltage is resistance times current. Or more practically, current equals voltage divided by resistance, because normally the voltage is given. And the whole thing has a name, Ohm's law. An experiment to demonstrate. The white lines indicate electrical lines. The voltage V is 24 volts. The lamp has a constant resistance of R, and as we see, a current of 84 milliamperes flows. If we double the resistance by adding a second lamp, the voltage at the source is still 24 volts. But the two loads connected in series have divided the current according to their resistance. So we have 2 times 12 volts. Because the current is also halved, namely to 41 milliamperes, the two lamps do not glow as brightly as the single lamp did. That is the disadvantage of this series circuit. As we can see, the parallel circuit is different. As each lamp is practically connected directly to the voltage source, the full voltage is applied to each load. And the full current flows through each lamp. Both glow brightly, as did the single lamp at the beginning of the experiment. For this reason, loads in electrical systems are normally connected in parallel. We have already said several times that current flows, but why does it flow? From where to where? Let's take a rechargeable battery as a voltage source. It has two connections, or more correctly, two poles, a minus pole and a plus pole. If we now connect a load to one pole, nothing happens. The lamp does not go on until we connect the other line to the second pole, because the current cannot flow until the circuit is closed. It does not matter how the lamp is connected. It goes on regardless of which way it is connected to the poles of the battery. The decisive thing is the potential difference between the poles. But why does the lamp illuminate, and why at different levels of brightness? Here too, Ohm's law provides the answer. The filament of the lamp has a resistance which we will assume to be constant. When a current of 12 volts is applied, a voltage of 41 milliamperes flows. Because of the frictional resistance, the filament is heated by the flow of electrons to such a degree that it begins to glow. If we increase the voltage to 24 volts, the current also doubles to 84 milliamperes. In other words, twice as many electrons are forced through the filament, and it gets even hotter. The lamp glows brighter. A word about electrical power. Here the same voltage is applied to both lamps, but one glows brighter than the other. The reason? Their power consumption is different. The less bright lamp is a 25-watt lamp, through which less current passes than through the brighter 60-watt lamp. The watt is the unit of measure for electrical power, and is the product of voltage times current. All electrical loads that work according to this principle and produce light and heat are called resistive loads. And here is a phenomenon that everyone knows, the short circuit. What happens exactly? If in an experiment we connect both poles of a voltage source directly, an extremely large current flows because there is no resistance. The result, extreme heat which leads to melting of the conductor or other damage. The solution? Fuses are integrated into electrical circuits. The fuse then interrupts the current flow and prevents further damage. So far, we have looked at two effects of electrical current, namely, light and heat. Another important effect is the magnetic effect. When a current flows through a conductor, it generates a magnetic field, the strength of which is proportional to the current. If the conductor is coiled, the magnetic field inside the coil is amplified considerably. Now, the strength of the magnetic field is dependent not only on the current, but also on the number of turns in the coil. The more turns, the stronger the magnetic field. If a soft iron core is inserted into this air core coil, the electromagnetic force is amplified considerably. This is the principle on which solenoids are based. Another phenomenon. If the soft iron core is movable, it is drawn into the middle of the coil when current is applied, thus producing a magnetic field. In this way, the core has the function of an armature. We will take a close look at this specific effect in the section on solenoid valves. The magnetic effect of current is the form of electrical energy most often encountered in electropneumatics and electrohydraulics. In relays, contactors, and solenoid valves. In contrast to resistive loads, these are called inductive loads. The electric motor also belongs to this category. A few words on the danger of electrical current. It is imperative that safety regulations be observed. Contact with live parts can be dangerous, even fatal. A short circuit can, as we have seen, have nasty consequences, a fire or a damaged system, for example. And then an important basic rule. Only authorized specialists should make changes to electrical systems, and, of course, only when it has been isolated from the power supply. Other protective measures. High-voltage cables are laid in such a way that no contact with them is possible, or so that no voltage can jump across. And current-carrying lines are insulated. And finally, low voltages are used wherever possible. That's all on the fundamentals of electropneumatics and electrohydraulics, in which various media, electrical current as the medium for control energy, and hydraulic oil or compressed air as the medium for actuation energy, complement each other ideally.